the notes that are there, I've already shared it with you on the Google Drive. I'll send the Google Drive thing as well. What do you exactly not understand, Logesh? Just let me know so that I might be able to help you. Did you attend all, have you covered all the material which is from the professor?
No, ma'am.
Then you should cover it, no? From those lectures are already there uploaded on the NPTEL online course. By only following the TA sessions, you will not be able to understand everything. I'll try my best to highlight the important concepts, but it is important for you to cover all the recorded lectures that are there from the professor on their NPTEL. Good afternoon, Vital. Thank you.
Where should I get the recorded section, ma'am?
You've enrolled for the NPTEL course, no?
Yes, ma'am. Yes, ma'am.
So they've given you a link where all of the worksheets, assignments, and the lectures are there from Professor Arnab Roy. That is what you've enrolled for. These are the sessions that we have once a week. Those are only for you to sort of get help in solving your assignments. This is not a standalone thing. I'll you have that link already because you've enrolled for the NPTEL course, right? So then they would have given you all the resources. They send you mails, right? That now the material for week 2 has been uploaded, etc., etc.
No, I asked to my professor, ma'am, whether you know any some of the people he did it.
Which
I didn't
professor?
done in this field in our college, ma'am.
Yeah, Vitul is helping you out. He's saying Swayam app. Vitul, please answer Logesh's question regarding where to get the material, and then we'll start the class. Thanks.
Where, ma'am? In Samayam app, ma'am.
Your classmates will help you. Just they will help you out regarding how to get it. If there's a link or something, then please just put it on the chat box. I don't have the link with me right
None
now.
of them here. None of them are my classmates there, ma'am.
Classmates in the sense that those who have enrolled in the course with you. These are not going to be in your college, but they have all enrolled in the NPTEL course. Okay, Vitul will send the link. Now we'll start the class. It's 3 already. If you have any problems, Logesh, then you just mail me separately. I'm not able to understand what is the problem. Okay. Um, okay, good afternoon, everyone. So today we'll be looking at a few important concepts which will be necessary for your next worksheet. One of them is the Galerkin method. The second terms in the transport equation, and third the concept of Taylor series. All of these things you might have heard if you've already completed a basic course on CFD or math. So this is just going to be like a brief introduction, and then we'll jump into the questions. Right. So first things first, we are talking about the Galerkin method. Okay, so what is the Galerkin method? So have you all heard about method of weighted residuals? Just answer in the chat box so that I know from where to begin. Okay, so I'll assume, okay, fine, no. So then we will talk about that. Right. Okay, so what happens is last time we discussed a lot about the governing equations, right? So governing equations are what? There's basically some partial differential equation. Just going to write some random partial differential equation plus phi equals to whatever. Okay, something is equal to 0. Okay, so then we will have some coefficients a, b, c, say a, b, c. So this is my governing equation. Okay, which is a partial differential equation. So I might not have the answer, like I need to find the phi. Okay, so there are multiple ways to do it. Once is like in your maths classes where you were discussing partial differential equation. In case you've learned, there are several mathematical methods. But for CFD, the most important method is that we assume, instead of finding an exact phi, we assume a phi. Okay, so assume phi. Let's call this phi dash. Okay, so we assume some phi, and then this assumed solution substitute in governing equation. In governing equation. This should be d square phi by dx square into a plus b into the same governing equation I've taken, and instead I have substituted my assumed solution. Okay, so why have I done that? Because I do not know my accurate phi, but I need to sort of get in the ballpark of that. So based on a certain criteria, I have decided some random phi, which is phi dash. Okay, so when I am looking at this, when I have substituted this phi dash into my governing equation, instead of 0, I get some finite residual r. Why? Because this phi, that is my actual answer, is going to basically be an exact solution to this governing equation. So then I will get a 0. Okay, but instead, if I'm putting some assumed solution, some guessed solution, then I will have some finite residual r. Okay, so what is my objective over here? I want r to tend to 0. Okay, I want to minimize r. That is my main concern. Okay, before I move forward with it, I think not everyone is following the material which has already been given by Professor Arnab Rao in terms of in the form of videos, recorded videos. Please follow that. Until unless you follow that, you will not be able to understand exactly where I'm coming from in all of these sessions. Okay, so it is absolutely necessary for you to follow the main course materials. This is the supplementary course material which we are just there to help you, but the main course is that taken by Professor Arnab Rao. So hopefully you'll follow the material carefully. Okay, so coming back, so I want my R to tend to 0. Why do I want my R to tend to 0? Does anyone have any ideas regarding that? You can answer if you want to. You can just unmute your mic and say something. If you don't want to answer, that's also fine. But it would be better if you would make this. Yeah, Akshat is right for exact solution. So we want a solution that should tend to my. If my r tends to 0, then my phi dot, that is assumed solution, will tend to phi. Okay. So yeah, thank you, Akshat. So basically this is my objective. Then how do I, so I want to minimize R. So there are multiple ways to do that. So one class of methods, okay, you can minimize R by different ways. So one class of methods is MWR, that is method of weighted residuals. Weighted residuals. So what we do over here is that we integrate my residual with some weight function. Okay, this is some weight function. This weight function can be anything depending on the subclass of the method. And then over the domain, over the entire domain, I do this and I put it equal to 0. Basically, I'm trying to minimize this R over the entire domain. Okay. So why we are doing such a long-winded method instead of solving this partial differential equation is because we cannot solve it. Why can we not solve it? Because we are looking at Navier-Stokes equations. Okay, so Navier-Stokes equations cannot be solved analytically until unless there are multiple simplifications. That is, you cannot just simply integrate and find out the answer. Okay, that is why we are going through with this method of weighted residual. Okay, so based on the weight, there are multiple classifications. If the weight function, if W equal to R, it's called method of least squares. Okay. If W equal to phi assumed, okay, then that is the Galerkin method. There are a bunch of other methods as well, but we'll just understand the spirit behind the method of weighted residuals. That is, you take your residual which you have obtained by substituting a phi dash in my governing equation. That residual, which is this R, I want to minimize so that I get my exact solution, so that I get closer to my exact solution. So once that is my objective, and how do I achieve it? I achieve it by through the method of weighted residuals. That is, I integrate the product of the weight function and the residual over the entire domain and set it equal to 0. So if my weight function is R, that is the residual itself, then it's called the method of least squares. If my weight function is this assumed solution phi dash, then it is called Galerkin method. Okay, so this is just some background on the method of weighted residuals. So we in this assignment, there are some questions regarding Galerkin method. So therefore, you should understand the workflow and how we are going about with it. So how we will try it is that first we will assume a trial solution which satisfies the BC. This is my okay. Then put in governing equation, put this phi dash in governing equation, and obtain the residual, which is my R. Okay. Residual should be 0 to every x. We will see if it can be directly put equal to 0 by some method. If it cannot be directly achieved through substitution or whatever, like in this step, then we will go to the next step. And what we will do is that we will multiply the trial function, that is phi dash, with the residual, that is R, integrated over the domain and set it equal to 0. Okay, so this is my Galerkin method. This is a method to approximate the solution phi. Okay, so CFD, which is the subject we are looking at right now, is all about approximation. We will not obtain the direct, the exact solution for our entire flow field. Okay, so what we try to do is that we try to get closer and closer to our exact solution through these methods, through these numerical methods. All of these methods together are called numerical methods. Okay, so basically what we do is that we see what we know already. We try to use what we know in order to get to the unknown. That is the way we go about with it. And a lot of it is based on approximation. So we want to make our approximation as good as possible. And method of weighted residuals is one of those methods, and Galerkin method is a subclass of that method. Okay. Then another topic that will be covered is about the terms in transport equation. So last time I think Aniket had asked what I mean by diffusive terms. Okay, diffusive. This question had come up. What is diffusive terms? And we had not been able to come up with a reasonable answer. So the reasonable answer over here is that when we have a spatial derivative, second degree spatial derivative, those terms are called diffusive. Why are they called diffusive now? Is because their tendency is to sort of distribute this, is averaging or smoothing. Okay, averaging, smoothing. Their action is diffusive. Okay, so whenever we see a term that looks something like this, that gives a second derivative in space, second derivative in space is diffusive. Okay, because it has an averaging action. It averages or smoothens the solution, right? Then the third term that we have over here is convective terms. The convective terms look something like this. V dot, this V dot is the velocity of flow. Let me take another color so that we don't get confused. Green. Right, fine. So velocity of flow is there, and this delta phi is the gradient of my function phi. Okay, that is not something that you don't know. So this sort of a term, whenever you see, that is called a convective term. Okay, why is it called convective? Because its action is to transport the property phi because of the flow. It moves it physically moves the property phi. Meanwhile, the diffusive term diffuses it. So the difference between it is something that we have done in the last class. That is when we have put ink in a flowing river, then it moves because of the flow. That is the convective action. When I put my ink in a still water trough, like I just put a drop of ink where the water, like I have a bucket of water, it's not moving, and I put a drop of ink there, then because of the difference in the concentration, I get a diffusive action, like the it just diffuses through the entire flow. Okay, so that is a diffusive action. This is just for you to get a physical feel. Is that okay? Okay. If you have any questions, then please feel free to interrupt. I will move on. Okay. Third concept of importance is Taylor series. All of you have looked at it in 12th standard or your basic engineering mathematics courses. Example for convective flow. Convective flow is like simply when you are physically the flow is taking one property from another. So convection, you've all heard of convection when we have that. This is like a hot plate. Okay, I have a hot plate over here, and there are this is at T equal to 600 Kelvin, whatever, okay? And my flow outside is 300 Kelvin, okay? So there are two actions that heat up my flow. One is through conduction, that the flow, like the molecules just next to this plate will get conducted, will get the conducted heat, and the other is that due to the movement, okay, that these molecules get heated, then they move upstairs, and therefore these the flow that is far away from the plate also gets heated. So this action is convection. Okay. Another example is what I gave the ink example the last time, that if I have a river and I drop a bucket of ink over here, okay, so then this ink will move in this direction. So that is because the flow is carrying the ink in that direction. Therefore, this is a convective movement of the property, that is ink. Convective motion. Okay. So difference, yeah. Yes, Akshay.
Ma'am, here in diffusive d2 power d2x by dx square, इसके
Yes.
बाद आपने यहाँ पे all even derivatives लिख रखा है, तो इसका मेन मतलब del 4 5 upon del x power 4 भी होगा तो भी इसका मतलब diffusive ही होगा.
Yes, you are right. Correct. So, sorry, all the even derivatives have the property that they are diffusive. Okay. This is just for your information. I've written it so that you do not get confused. If you see d4 by dx4, and that is also called diffusive, right? Okay, moving on to the Taylor series. So we've all seen that. So basically, Taylor series is also a numerical method to approximate the function at a certain point. Okay, so if I have this value, that is function at any point x, okay, and then I want to know what the function at x plus delta x is, then how do I go about it? Taylor series tells me that I can approximate it through through my derivatives, f dash x, f double dash x, f triple dash x, and f whatever that goes up to n, and using my delta x. Okay, delta x is my step size. Okay, you see the step size in multiple ways, right? Because we get, like, we talk about time step sometimes, that is delta t. We talk about our grid size, that is delta x, because delta x, delta y, delta z, etc. are basically like motion in the space, while delta t is the motion in time. So anyway, you don't have to worry about what kind of delta it is, whatever the step size is, whether spatial or temporal. You can use this Taylor series to get the answer for the function at the next step. Okay. So basically, using this is a very powerful. Okay, it's very important. Very powerful law or theorem, whatever. This is a very powerful formula that is used in CFD. Okay, because every time we are talking about approximation, and when we are talking about approximation, we need to find the unknowns using the knowns. Okay, so then you can obtain the expression for all derivatives, that is f double dash x, f dash x, f triple dash x, etc., etc. You can obtain the expressions for all of these derivatives in terms of the function values, that is f dash x, x plus f into, sorry, fx plus delta x, that is the value of the function at x plus delta x, and value function of fx using mathematical manipulation. Okay, I can choose my delta x to be minus delta x as well. Okay, so based on that, I can just recreate the Taylor series in several forms, and because of that recreation I can use mathematical manipulations in order to get the values of these derivatives, okay, because mostly we don't have the values for derivatives. We'll see. In CFD we typically have to find the derivatives using the function values at cells, okay. Anyway, it can be in either direction. So, but the most important thing is that this Taylor series is something that you should understand and remember every time. Okay, whenever we are dealing with CFD. Right. Okay. So based on whether my delta x is positive or negative, I have forward or backward difference. If my delta x is positive, that is I'm moving forward in space or time. Okay, I'm going to the next step. If it's negative, then I'm going to the previous step. So therefore, for the forward difference, the delta should be positive, and for the backward difference, the delta should be negative. So using both of these simultaneously, that is, I use delta x and positive delta x and minus delta x together, we get the central difference. If you have gone through the material that is provided by the NPTEL lecture, that is the recorded lectures, then you will know where this comes from. Okay. Once again, I'm repeating. It's very important that you go through the material that is already provided to you in terms of recorded lectures by the professor, because only then will you be able to follow whatever we have over here. And feel free to ask any doubts that you might have come across during your when you're learning through those lectures. Right. Okay. So we already discussed this. Now we'll jump to our questions. Okay. So here I hope you're able to see this clearly. Wait. Okay. So let's read the question. Numerically approximated values of f dash x, okay, this is my one information, is equal to 180.84 at x 2.2 using the step size, that is my delta x, this is my delta x is equal to 0.4, okay. Which of the following methods is used to find the derivative for the data given in the below in the table? So I have my data for fx, fx plus delta x, etc. Okay, so I have my data for for the function at different x values. Okay, so my function is I'm giving my function. My function is e raised by 2x. Okay, so it's asking me that if I'm getting such a value for f dash x, if my f dash x is equal to 180.84, then which method have I used to compute it? Okay, first it's an analytical method, that is you simply used d by dx of e raised to power 2x at x equal to 1.4. Please quickly compute it and give me the answer in the chat box. Good, very good. Thanks, Vipin. 162.90. So 162.90 is not equal to my 180.84. So I have not used the analytical method, not used this. Now let's look at what the backward difference means. Okay, backward difference. So based on whatever we discussed regarding the Taylor series, f dash x is given by fx minus fx minus delta x by delta x. Okay, this is something that I remember because I have derived this many times. This is a fairly standard thing that you might have also seen during your earlier classes or even your school or whatever. So this is the formula, okay. So if you want to, then you can derive it on your own as well using the Taylor series. But this is a fairly standard formula. You can remember this, okay. This you can remember. We'll just put a box around it so that you won't be confused, right? Okay. So now please compute for this as well. Wait. I'll just write down the expression what it's supposed to be. It's supposed to be e raised to the power 2 into I have to find it at 2.2, right? So 2 into 2.2, okay, minus e raised to the power 2 into 1.8 by 0.4. So this is what I need. Now please compute that. Yes, Mandish, I will share the drive link. Just a second. Please compute this as well and write the answer in the chat box. You have all of the data over here. You don't even need to compute this. I'll just write this down. Okay, great. Thank you for the answers, Bhuti. That is 112.13. So this is also not my answer, okay, because 112.13 is not equal to 180.4. So next I have central difference. So what does f dash x look like in central difference? Let's have a look at that. F dash x looks like f x plus delta x minus f x minus delta x. See, we spoke about how if we use both plus and positive and negative delta x, then that is central difference. Okay, so here we are doing that. So this is my formula. Okay, so that is e raised to the power 2.6 minus e raised into 2. Sorry, this was 2 into 2.6 minus e raised to the power 2 into 1.8. Okay, great, Shruti. Thank you for that. So that this is my expression and I'm getting the answer 180.84275. Okay, so this is what I have. This is right. Okay, so this is equal to whatever my question asked me. My question was like, what method have I used if my f dash x is coming out to be 180.84, and clearly it's central difference. Okay. Just for your information, I'm also writing down the expression for forward difference. You can evaluate too. It's pretty simple. You would have understood what that expression should look like by now. Right, yeah. Okay, so this is what the expression for the forward difference looks like. So you can compute it on your own. You have the data already. Okay, let's move on to the next question. Okay, so this question is something that will give you a visual idea of what we mean when we are talking about various like forward difference, backward difference, central difference, etc. Okay, so let's read the question. What is the correct order of finite difference expression? Sorry, of finite difference expression with respect to the finite difference modules, that is illustrations. Okay, we mean over here that whatever photos we have shown in the figures below. Okay, so it's telling me that what picture should I match with what depiction over here. Okay, so let's see what my picture is talking about. So in this, the orange dots, whatever there are there, these orange dots, represent the data points we have used. That is which x or y have I used. This is in 2 dimensions, so then there are 2 independent variables, x and y. So it's right. So it's asking me that these orange dots are telling me that which x and y I have used. Okay, so let's see. So over here, let's start with something simpler. This looks easier to me. This is like a fairly simple thing. So what has happened is that I have used my j is j, and then the other y that I have used is j minus 1. So instantly, since it's a backward movement, I know this is a backward difference. Okay, backward difference. So let's see where else in this entire set of formulae I use backward difference. Okay, this is, what is this? This one is like a no, Vital, it's not D. In that we are using like a double situation. Backward difference is this third. Okay, so I can match my C to 3. Okay, this one I have matched. These two are the options that I have. Is that okay? Do you understand why that is the backward difference? Because over here the J, I hope you're able to see it, otherwise I'll zoom it in. Yeah, that was j minus 1. That is my y has moved one step backwards, and these are the only 2 data points that I used. So 2 data points, another way to know that is that 2 data points have only been used in this and this example, the B and C, right? But over here, only the backward step is used. Over here, the backward and the forward step is used, which by our definition we know is central difference. Okay, so this is central difference, and this corresponds to D. Let's match the correct. 3 is C, 2 is D. Let's see where else have 2 got D. So now the D option is correct, so now I know that. So similarly, you can just see what is happening in the other problems as well. So, okay, what has happened over here? Here I am using 3 data points instead of 2. Okay, therefore this D option and B option are different from each other because here 3 data points have been used. So therefore, and since I used 3 data points, so here I am able to get the second derivative. Okay, so this is B. This is just for you to get a visual feel of what we are doing. Okay. And for the fourth option, this one uses 4 data points. So I have 4 data points, 1, 2, 3, 4, and they're diagonal, like basically both my x and y are changing. So I'm getting a derivative, the second derivative, in which is a function of both x and y. Okay, the second derivative, mixed second derivative as we call it. Okay, so therefore this is my correct option, D. Okay. This is just for you to understand that when we are looking at different formulae using whatever forward difference, backward difference, or whatever we are using, what are we exactly doing in terms of grids? Because later on in CFD, as you might know, we will be looking at mesh, right? A mesh that is a sort of like a grid like this. So when we look at a grid, if I'm saying that okay, I'm using forward difference, then you should know that I'm traveling in this direction. Like if this is 1, 2, 3, 4, then I'm traveling in this direction when I'm using forward difference. I'm traveling in this direction when I'm using backward distance, and I'm using both if I'm using both forward and backward, then it's central. So this is just some visual aid for you to realize what we're talking about. Okay. Right. Okay. So this is some, right.
मैम
Yes, Akshat.
मैम ये इस वाले क्वेश्चन में मैम जो फॉर्मूला है मतलब जो
जी।
ऊपर वाली टर्म्स जितनी है जितने हमारे पास ग्रिड पॉइंट होंगे
उतने हमारे पास ग्रिड पॉइंट होंगे। हाँ, तो यहाँ पे क्या हो रहा है कि बेसिकली हम ये देखने की कोशिश कर रहे हैं कि कौन सा डेटा पॉइंट, मतलब हमारे पास कुछ डेटा पॉइंट्स हैं, ठीक है, ये है ऑरेंज वाले जो है वो सारे डेटा पॉइंट्स हैं, तो कौन से डेटा पॉइंट्स मैंने यूज करके ये डेरिवेटिव्स निकाले हैं, ठीक है, तो वो आई एम ट्राइंग टू चेक दैट. ओके, so Taylor series once again is an important part of this entire whatever we are doing over here when we are calculating derivatives. So basically we are looking at for that Taylor series which data points did we use to get to this expression. ठीक है, we will apply some mathematical manipulations to our Taylor series using certain function values, and which are those function values is our question. Okay.
बट मैम अगर ग्रिड पॉइंट बहुत ज्यादा हुए तो
तो then we will be moving in like moving in a स्टेप वाइज फैशन. ठीक है, ऐसा नहीं है कि हम सारे के सारे यूज करेंगे, हम उतने यूज करेंगे जितने हमें मिनिमम रिक्वायर्ड है. अगर मेरी मिनिमम देखो, जैसे इस इन द केस ऑफ सेकंड डेरिवेटिव, माय मिनिमम रिक्वायरमेंट इज दैट आई नीड 3 डेटा पॉइंट्स. ओके, विदाउट 3 डेटा पॉइंट्स यू कैन टेक दिस एज अ होमवर्क आल्सो इफ यू वांट. कंप्यूट f double dash x using Taylor series. ठीक है, so when you do this exercise, I strongly recommend that you do it. Okay, so what you have to do is that you will have to take f x plus delta x, उसका पूरा Taylor series expansion. You will have to take f x minus delta x, the whole Taylor series expansion, and you need to eliminate everything that is not the second derivative. Okay, so basically I need to cut down my first derivative. Delta x by square by 2 f double dash x and so on and so forth. I'm not writing the entire thing because my entire thing is not required over here. So basically minus f dash x into delta x plus delta x square by 2 factorial f double dash x. Okay, so then you tell me that when I'm looking at this, so which all terms will appear in my final solution. Okay, I'm telling you already which all terms will appear. This will appear, this will appear, and this will appear in my that is 3 data points, x plus delta x and x minus delta x will appear in my expression for f double dash x. Okay, so when you do this exercise, you will realize that what is happening over here. So we are not using all the grid points that are there in the mesh. We are using the minimum possible grid points required to get the accuracy that I need, okay, or to get the expression that I need. If I want it to be more accurate, then I can use 10 grid points also, but that's unnecessary. I don't want to do that. Okay, like it's a lot of extra work and you don't have to do it. So basically you can use the Taylor series to come up with the expression for the whatever f double dash x or mixed derivatives and everything, and when you do that you will realize that we are using the minimum possible points for my desired accuracy. Okay, so it doesn't mean that if I have 20 points, then I will use 20 points in this expression. Not at all. I'll use 2 only. And then I will use the next 2 points to come up with the du by dy at the next location. Is that okay, Akshat?
Oh, yes, ma'am. Understand.
Thank you. Okay, right. Then we'll go with this. So this you should know. So I need an answer from the class. Okay, what type of boundary condition is depicted in the flow below? I'll just put it into words. What is it? What do we have over here? Flux, that is heat flux, or just let's just say flux, is exiting the boundary. What type of boundary condition is this? You should know this since you have followed the material, right? Now Dirichlet is the wrong answer. Newman, correct. Jagdishan is right. It's Newman. See, I'll give you the definitions for Dirichlet and Newman. Dirichlet is when the function is specified at the boundary. An example, a physical example in that terms would be that if I have a box over here and I say that at the boundaries of the box that I have over here, that is at t equal to 600 Kelvin. Okay, this is a Dirichlet one. Why? Because I have directly told you what the function's value at the boundary should be. Newman is flux of the function, or let's, instead of function, let us say property. When the property is a better word for this. When the property is specified at the boundary, flux of the property, that is, if the property is flowing, then with what rate it's flowing, property is specified. So since my Q is basically a function of dt by dx, okay, so then this is what I've been specified over here. So it's function of dt by dx, that is the flux. So I have value for that. That is why it's called the boundary. Okay, so you just need to know about that. So instead of giving you the exact value of the temperature at the boundary, if I give you the rate at which heat is flowing out of it or into it, then that is a Newman, sorry. Okay? And these are those definitions you should know. Right, great. Okay. Okay, so now we are coming upon a question on Galerkin. Yeah. So if there is a given human BC, then both sides should be gradient. Both sides, what do you mean by both sides? Can you unmute and talk to me? I did not understand the question, Vitul, so if you could explain it, or you can take it up with me later. Then I'll move on to the next question. Okay? Time is limited, that's why. Okay, so now we are coming upon an important question that you might face in your worksheet or assignment. Okay, a physical phenomena is modeled using the following differential equation. Okay, this is a differential equation. This is ordinary differential equation. It's not a partial differential equation. It's an ordinary differential equation. And I'm giving these two boundary conditions. Okay. Where x is this is my domain. Let's just name everything so that you're okay with that. Assuming y cap, this is my assumed solution. Okay, this y cap is what I had earlier mentioned was like the, wait, assumed solution. Assuming y as a trial function, determine the value of the parameter C0 using Galerkin's method of weighted residuals. Okay, so we'll go about it in a systematic manner. What we'll do is, first check if trial function satisfies BC. So y cap is equal to what? C0 into x minus x4. So that's equal to 0. This is my boundary condition. Okay, this is my this one boundary condition. Does it satisfy the boundary condition? If I put my x equal to 0, yes it does. It's very clear. Okay, not an issue. So anyone is similar. Great, thanks Shaktishan. So for the other boundary condition as well, this is being satisfied. 1 minus, because 1 minus 1 is the power 4 is 1. This is 0. Okay, so I'm getting no information about, let's just write, no information about C0 from boundary condition. Okay, then what will be the second thing that I'll do? Second thing is I'll see if I can directly substitute this function in my ordinary differential equation and get the answer to my problems without much trouble. Let's see. Because I just need the C0's value. I need the value for C0 such that this ordinary differential equation is true throughout the domain. That is my requirement because we want the residual to be 0. x4 plus 500 square is equal to 0. Can you solve this for me? Okay. So let's just, okay, great. Thanks, Alfina. That's great. So basically what we did is, the right answer, thank you. What happens is that I double differentiate it. So what I get from that is that I get, first this will be when the first differentiation will become 1. Then I'll get dy dx equals to 1 minus, I know you all know how to do it, but I'm just repeating it for the benefit of the class, thank you. And right, minus 12 into, sorry, I missed the C0, right, C0 into x square is equal to minus 500 x square. So here I can directly cancel out these x square and then I won't have to worry about whether it's true over the entire domain because it's giving me an easy way out. It's already telling me that if you substitute C0 as 41.66 as Alfina said, so then I will get my my ordinary differential equation will be true throughout the domain. So I am happy with this answer. This is my answer. Okay. So basically we had mentioned 3 steps in the beginning for Galerkin method. Let's revisit that. Assume trial solution. So assume we had already gotten a trial solution. Put that in the governing equation and observe residual R. If it cannot be if it cannot be achieved directly, use trial function as the weight function, and then put it equal to 0. So, but we were able to achieve it directly. Fine. So, since we were able to achieve the value for C0 for which this ordinary differential equation will be true throughout the domain, I don't really need to care about the third step, that is the Galerkin substitution. Fine. So, over here, I'm happy with this. This was a nice and easy question for me. Okay. So, then we have another question of similar type where I'm given a different ordinary equation, an ordinary differential equation once again, and I'm given 2 boundary conditions at 0 and 1. So what do I have to, what is my assumed solution? That is, assumed solution is C1 into x minus 1 plus x. Okay. So determine the value of C1 using Galerkin method of weighted residuals. First I will put in BC. See if y cap satisfies BC. So then my y should be 0 at, let's go with the first boundary condition, y 0 equal to 0. Is it 0? Is my y cap equal to 0 at 0? Yes, it's 0. Okay, I don't mind. Then is my y cap equal, y cap, so my y cap 0 at 1. Yes, that's also true. Okay, 1 into 1 minus 1. Oh, sorry, it's 1. Yes, that's 1. So this is 1. Okay, so both of my boundary conditions are being satisfied. So I get no information on C1. Okay, so then I will move on with towards the next step. Next step, what I'll do is I'll have to unload the page over here. Let's just see. Right. Next up, I'm just going to put it in my governing equation. Put in governing equation. In OD, I'm just going to write OD for our ease of understanding. So let's do that. Where have I done that? What is my OD? D square y by dx square plus y equals to 4x. Okay. So then this looks like, once again I want you to simplify this for me. I've already, I'll just write it in terms of this. Okay. So please just simplify this in your notebooks. To C1 plus x, is that what you're getting? Will you get the x? Okay, let's just do it. This differentiated once. Let's keep the d by dx over here. We'll get 2c1x, okay, plus c1. This x will go away, right, because it's d by dx. Plus c1x square minus c1x plus x equal to 4x. So then let me do this again. Then we'll get 2c1 plus c1x square minus c1x plus x equals to 4x. So what I will finally get is, let me just arrange it in terms of this, minus 3x, because my 4 comes to the other side, minus c1x plus 2c1, right? So this is what I'm getting. Can I directly get a solution for c1 from this? Can I? No, right? We can't get a solution for the C1 as easily as we could get in the other one, last problem. So then I have to move on to my third step. That is my method, Galerkin method. It's going to be a longer problem to solve, so I'm not going to do all of the maths right now. I would recommend you do it on your own and you just follow the methodology, like the stepwise methodology while answering your questions. So now what do I want? WR equals to 0. What is my weight function? And you can answer in the chat box. For Galerkin method, we discussed it at the beginning of the class. That method, there are multiple types of method of weighted residuals. Okay, so Alfina, it's not x. What it is it's going to be y cap. Why is it y cap? Because we discussed in the beginning for method of for the Galerkin method, my trial function, that is, sorry, the weight function is equal to the trial function. Okay, so this is the definition of Galerkin method. There is no logic that why is it y cap, okay? Yes, Akshit, it is what you are saying. The weight function is equal to the assumed function, that is c1x square. Let me change the pen color again, sorry. c1x square plus c1x, this is what it is, right? Just a sec, sorry, minus c1x plus x, okay? Then what you need to do is that you need to integrate it from 0 to 1. We'll take your weight function, which is this, and you will multiply it with your residual, which is this, okay? This is my R, this is my W, oh sorry, right? So I'm just going to put it over here. I will not go through with the entire maths of this, it's a fairly long thing and we need to get a move on. This you need to put equal to 0. This is going to be a, yes Hamza, you can speak up if you don't understand something. Okay, so what you do, you can speak up Hamza anytime, that's not a problem. I hope you can unmute yourself. I do not think there's a restriction on that. Right. Okay, so you just multiply all of these terms, then go through with a normal integration with respect to x. Wait a second. Okay, and then equate that to 0. Because this is a definitive integral, that is you have a lower limit and an upper limit, you will be able to get a fixed expression and your x will disappear, and then you can find out your c1. Okay, so just go through it, solve it properly, and this is the methodology that you have to follow for all Galerkin methods. It's going to be a little long and it's not important for me to tell you how to integrate x, I'm pretty sure, so therefore I'm skipping this part, but you go through it. Is that okay? Basically, the workflow for these sorts of problem is, first you see if the y satisfies the boundary condition. Why am I doing that? Because that's the easiest thing to check. Okay, if it does not satisfy the boundary condition, then I'm just going to throw my trial function away. I'm going to choose another trial function. Then I put it into my governing equation, and then I get a residual. If I'm able to directly put the residual equal to 0 without much issue, and I'm able to find out the constant that I need, then I'm okay with it. Then I do not need to go through with the Galerkin method. But then the next part is to find it using any method of weighted residual. Actually, we are using Galerkin method because that's what the question asked us to do. Otherwise, you can choose another weight function as well. But here, since we are asked to use the Galerkin method, we are using the weight function, which is equal to the assumed function. Okay, this is the workflow you have to follow. And then integrate it over the entire domain and put equal to 0. Yes, Akshay.
मैम यहाँ पे जो कंडीशन लगाई
method
क्वेश्चन से ली हुई है ना 0 to 1
जी ये
like this.
here we have a domain over here, ठीक है?
Please repeat.
Is that fine?
यस मैम
Okay, thanks. Yeah, right.
कौन सी कंडीशन भाई? 0 is equal to 0 is equal to 1.
No, he is asking about the domain because I integrated it from 0 to 1. So over the domain is
Where 0
0.
less than x less than 1 is
That is the
given
x is
equal
ranging
to
from 0 to 1.
c1 x into x minus 1 plus x. The trial function determine the value of c1 using
Okay, I hope you understand that. Then, okay. So next we'll move on to the next question. What will be the first
literally I didn't understand because y is equal to c1 x into x minus 1 plus x.
This is what we've given in the
If y
question
satisfies
already.
BC,
Boundary conditions. These are the boundary conditions. You joined the class late, right? So this is the workflow that I've explained already. If you have any problem with the with the questions and all, then you should mail me separately because we've already moved quite a bit in the class. We only have like around 6 minutes left. So I need to cover up. Best solution for C1. Yeah, basically we need to just integrate this entire, like go through with this integration, put it equal to 0, and then we will get the answer for C1. So what the answer is, that you can compute on your own. I have not gone through with the with the entire thing, but just trust whatever your integration is. Otherwise, I'll just tell you what the answer is. I did not check it out. Yeah, that's fine. Okay, thanks. What will be the first order accurate forward difference approximation for d4f by dx4? Okay, so here what I'm asked is that I need to find out the forward difference approximation. That is, I can only use positive forward. What does forward difference mean? Delta x is positive. Okay, of d4f by dx4. That is the fourth derivative of the function f. Okay, so we will recall our Taylor series. Okay, I'm just going to write some things down first. We're running a bit short on time, but let's just write the Taylor series expansion for, let's see what all is already given in my options. I have been given fi equal to 4, I plus 4, that is 4 time steps have been moved, have been traversed. I have been given fi plus 3, that is 3 time steps, that is delta x equals to, let's just write it, I'm sorry. Fi plus 4 means delta x is equal to 4 delta x, okay? That is my, let's not, that is, the step size, let's call it a step size. No, Akshat, that's not right, and you have to go through it with a little, this is going to take some time, you cannot guess it. So, what do we have? We have another answer, that is B. Let's see what the answer is. Negative, negative. Right. Okay. Right. Okay, so you compute the answer on your own, but I'm just trying to tell you that the step size is going to be. And on what basis are you giving these answers? I would like the reply. That everyone's giving different answers. So how did you come up upon your answer? Okay, this is the information that I have. Right. So you can write the Taylor series for each of these. I'll just write it for f equal to 4 just so that you have an answer. F delta x. Should I write it for all of these functions, the Taylor series? Do you want me to do that? Because you'll have access to this document later. So if you want me to do that so that you can follow up, that would be nice if you can tell me. This is already, okay, fine. I'll write it down then for you. So you see, why am I putting these coefficients 64 and 4 and everything? Because here my step size is 4 into delta x. What is being said? I have calculated fifth derivative already, and here the logic is alternate positive negative term will have higher value of coefficient. Alternate. Okay, that's good. Basically, what you need to do, I'm just going to write it down for the benefit of the class, whatever this thing is. Right. So for fi plus 3, this is fi plus 3 delta x. So you see how the powers are going. This will be 9, this will be, it's all based on my Taylor series. This will be fairly easy for you to work out. So I'm not writing down for fi plus 2 and fi plus 3. So just, sorry, fi plus 1, that you can do on your own. Suppose question mark fi plus 1 equal to question mark. So basically what we need to do is that since this term only has like function values that are fi plus 4, we don't have any fi dash values, right? We don't have any derivatives in this expression at all. So what we want is for all the derivatives except f4, except what I require, to go to 0. Okay, so I'll write down what we need so that we can see. All the derivatives derivatives which are except just except f4 should mutually cancel out. Okay, why do they need to cancel out? Because they don't appear in my expression at all. Okay, cancel out. So multiply whatever the coefficients are written over here, multiply the coefficients, Taylor series coefficients, let's see. So multiply the Taylor series coefficients with the factors that are given in this formula, factors, and see if they cancel out. Let's just do it for the simplest thing. Let me match my factors for the okay. So let's see. I'm going to match the coefficients for the first derivative. Okay, 4, 3. This is going to be 2. That is simple, and it's going to be 1. Okay. So what I need to do is that I need to multiply my 4 into 4. Okay, this is my Taylor series coefficient plus oh sorry, not 4, 1 into 4 plus 4 into 3. Let's not put plus, we'll see whether to put plus or minus. 6 into 2, 4 into 1, right? 4 into 1. This is a typo over here, this should be F and this should be 4. Right. 4 into 1. So they should all cancel out mutually. Okay, this is for coefficients of f dash I. Okay, so how will they cancel out mutually? This is 4, this is 12, this is 12, this is 4. So I need to put minus sign where? Where should I put the minus sign? I put over here and put over here, right? Or rather, since we have alternating signs as approval sign, so then we have this. So basically, you will see that the second term should have the negative sign, the third term should have the positive sign, and this should have the negative sign. So this is my correct answer. B, approval is right. Okay. Then let's move on to the next question. So you understand what the thought behind it is? The thought is so that we don't, like, since we are not able to see any of the other derivatives, that are f dash x or f double dash x, etc., in my final expressions, then that means that they will all mutually cancel out with each other. Okay, so I just need to pick up my easiest whatever coefficients that I have over here and try to cancel it out. You can repeat the same exercise with coefficient 16, this one, the coefficient of f dash x as well. Okay, they will also cancel out, but that's like a tougher thing to do, so I will refrain from doing that. Right. Okay. So we're running short on time. If you want me to continue with this question, then let me know. Otherwise, we can end the class. You can read the question and see. Any opinion on that? Continue. Okay, great. Then, okay, so let's see what we have over here. We have for function y equal to y of x sine 2 pi x. This is what I have. Okay, what is the percentage error between the exact value and the approximate value for dy by dx at x 0.6? So let's see what the exact value is. Okay, exact value for dy by x, exact value. So what do we mean by exact value? Exact value is the analytical value. So y dash x is equal to, can I get the answer for this? Using your normal differentiation.
2 pi cos 2 pi x.
Great. Yeah, very good. Okay, so this is the answer. Fine. So I need to compute it at 0.375. Please give me the answer for y dash at 0.375. Okay. So can this compute it using your calculators? It's minus 4.44. Oh, is it 6.227? I don't think so. 2 pi into, this is in radians. Whenever you're not given the, it's supposed to be in radians, everyone. Hopefully I have not computed it incorrectly, I'll just compute that. So 2 pi into cos of 2 pi into 0.375, and this has to be in radians. Okay, that is coming out to be minus of 4.44288. Okay, so just try to compute it again. Hopefully I have not made a mistake, but I don't think I have. So just see if this is the right answer. Okay, yeah, you have done it in degrees, Akshat and Jagdish. So you have computed this in degrees. This is supposed to be in radians. Okay, whenever your until is mentioned, just take it as radians, right? So this is my value. Okay, use your calculator in the radian mode. Fine. Then, yeah, great. Thanks, Mayank. Fine. So now we need the approximate value. Using central difference is what they've told us. Approximate value. Let's see what other information is given. We have been told that the grid size is 0.05. What does that mean? Delta x is 0.005. Okay. So it says now I need my derivative value in terms of the central difference. So that is x plus delta x minus f of x minus delta x by 2 delta x. So that should be sine of 2 pi into 0.38 minus sine of 2 pi into 0.37 by 2 into 0.005. Okay, so just compute the approximate value on your own and find the percentage error. Okay, this is already almost complete, so I'll jump to the next question. You realize what we're doing over here? Here we just try to see what all information is given to us in the question. So we had the yx, so we could find the exact value for the derivative. Then we did the percentage error that you will get on your own, and it's asked us to compare the exact value and the approximate value. We're able to get the exact value because we know what the derivative of sine x is, okay, and sine 2 pi x is. So, and the approximate value, it is asked us to use central difference for the approximate value. So, central difference formula is this. Okay, this is my central difference formula. Therefore, I used it. Then I will compute my values for the function at x plus delta x and x minus delta x, and then I will get my answer. Okay, great. Fine. In the finite volume method, a control point at which flux has to be calculated by interpolation is a point located as. So the answer for this is face center of the volume. This is just something that it just is. That is how it is. Basically, what we have is when we have a finite volume like this. Okay, whatever. It's not great. Wait. Wait. So when I have a finite volume, this is my finite volume. This is basically a cell because it's a finite volume. That I can call it a cell. I can call it a control volume. So all of these things are the same thing. So I need the flux values I think I spoke about it in the last class as well, but your function values are at the center and the flux values are at the face. Flux values. So where will I compute these flux values? I will compute it at the face center. Okay. There's no point of me computing the flux values at the top and bottom when my center is matched like this, the face center. This is something like this that just is, so I don't have any reason for this as such, but basically the point behind that is that we find out the flux at the face center. Meanwhile, we find the function values, that is the property values at the cell center, that is the center of the volume. Okay. Which of the following dimensionless numbers is related to transportiveness? Okay. So anyone has any ideas on this? What is the Courant number? D. Great, Shipra. Okay. So then I suppose we have an idea of this. So yeah, great. Okay. So then already everyone has an idea of what these numbers mean. So I'll just quickly write down what each of these are related to. This is a stability criteria. This is inertial versus viscous forces. Now the number is convective heat by convective, not heat, just convective versus conductive property transfer. The Peclet number is advection. Advection and convection, this is called convection. Convection by diffusion. So we saw these terms, convection and diffusion, both appear in our the transport equation at the beginning of the lecture. So therefore, Peclet number is related to transportiveness, right? Okay, so now this is another question that you should get, which I will not answer for you. Which of these following option defines the movement and the Dirichlet boundary condition? Okay, so this we have already discussed, so you should know the answer to this. I'll just zoom it in case it's not very visible. Great, thanks Apollo. This is correct. Okay, why? Because Newman is basically the flux and Dirichlet is like when you specify the property boundary. Okay, thanks. At two intervals, Newman conditions, I do not understand what you mean by intervals. Do you mean cells, Nitin? See, you will not, these are boundary conditions, Newman and Dirichlet. Okay, so if I have, this is a bad volume, just a sec. Okay, so if I have this domain, then I will have my boundary conditions only at the boundaries. Okay, so it will not be like each cell is going to have a separate boundary condition. Boundary condition is at the domain boundary, which is why it's called the boundary condition in the first place. Right? So over here, what we're going to have is that we can I can specify this whatever property UP, either I can specify UP or DUP by DN. Okay, where DN is this normal vector. Okay, so since if this is called Newman, this is called Dirichlet. That's about it. There's nothing too complicated about it. Hopefully we understand that boundary conditions are only going to be applied at the boundaries. Okay. Then in finite volume method we deal with dash form of conservation equations. So any ideas on this? Great, integral, right. So I suppose this is something that is clear. Okay, this is the last question. General transport equation for property phi without any source includes which of the following terms? Let's just write the form of this. This is, we're going to write a random property phi. You can answer in the chat box if you have already got an idea of what it's supposed to be. This we already talked about in the beginning of the class, so it shouldn't be much of an issue. No Manikam, that's not right. Yeah, Alfrena, that is right. All of the above. All of these terms make an appearance. Okay. This is what we discussed in the beginning of the class. This is the unsteady term. This is the convective term, and this is the diffusive term. So if you have had a look at the Navier-Stokes equation, this is the source term, but here it has been specifically noted that there is no source term, so this goes, so this is not going to be a part of my answer, okay? But, right, but this is what my generic, let's just put some coefficient C over here. This is what my generic transport equation looks like. Now some of these things might be missing, or they might not apply to a certain property, but this is what a general transport equation looks like. Okay, so then unsteady, convective and diffusive, all terms are being seen over here in my general transport equation. Is that okay? So now we are done with the questions for today. Do you have any other clarifications or something that you would want me to repeat? If you don't have anything to ask, then you can leave the session, no problem.
मैम
Yes, Akshay.
मैम आई वांट टू आस्क यू अबाउट द फ्लक्स, मतलब मैं जो फ्लक्स का मतलब समझता हूँ कि
जी.
मतलब कोई भी फ्लो रेट विद रेस्पेक्ट टू एरिया देखता है, या
ठीक है.
फिर इसके अलावा कोई इसका मतलब है?
नहीं, फ्लक्स का आप ठीक कह रहे हो कि कोई भी प्रॉपर्टी कितना फ्लो कर रही है, मतलब फ्लो रेट अक्रॉस अ बाउंड्री विद रिस्पेक्ट टू एरिया. यू आर राइट इन दैट फ्लक्स इज फ्लो ऑफ प्रॉपर्टी पर एरिया यूनिट. ठीक है, तो यू आर राइट इन दैट रिस्पेक्ट, योर अंडरस्टैंडिंग इज करेक्ट, पर यूनिट एरिया. राइट, दैट्स द करेक्ट डेफिनेशन ऑप्शन. या
एंड मैम आपने जो लास्ट क्लास में आपने जो जेनरिक इक्वेशन बताई थी ना मैम, वो जो
जी.
क्वेश्चन सोल्व कर रहे थे, इसमें आपने बोला था कि बी स्क्वायर माइनस ए सी जब होगा इक्वल जीरो, लेस देन जीरो, जो थ्री कंडीशंस बताई थी.
जी.
तो मैम जो लेक्चर्स थे ना उसमें मैम बी स्क्वायर माइनस फोर ए सी दे रखा था.
देखो उसमें दैट इज फाइन. Essentially what the difference between the lectures and my information would be कि मैंने अपनी जेनेरिक इक्वेशन में जो इस चीज का कोफिशिएंट था मैंने 2D लिख रखा था. ठीक है, सो आई थिंक आई फॉलो डिफरेंट बुक और समथिंग, तो माय कोफिशिएंट वाज 2D. ठीक है, तो इसलिए जब मैं इसको स्क्वायर करती हूँ तो वो 4B स्क्वायर माइनस 4AC हो जाता है इक्वल टू 0, तो फिर मेरा 4 कट जाता है इसलिए एसेंशियली. ठीक है, क्योंकि 4 फैक्टर बाहर निकल जाता है. तो डोंट वरी अबाउट दैट. मेरे जो मैंने जनरल फॉर्म दिया था तुम्हें, in that I had put the coefficient of dou phi by dou x by dy equal to 2b, which is why my generic equation looked, which is why my conditions looked like b square minus ac instead of 4ac. ठीक है, is that okay? It's only a matter of how you take the convention. Is that okay?
या ओके मैम.
Great. So don't get confused by that. Pay attention to what your general equation looks like. If your general equation looks different than mine, then your condition is also going to be different. Okay? So, but just follow one method. Don't follow multiple methods. Yes.
Ma'am, diffusion and convection.
Yes.
Difference. What is the difference between diffusion and convection?
Okay. So, okay, let's see. Physically, let's see. Okay. I've given the same examples. I'm going to give it once again. I feel it's very intuitive. So, if you have like a tray of water, ठीक है? Thank you everyone. You can leave, no problem. Right. So I have some water which is still over here. Okay, Shipa? Then what I did, I put some ink into it. Okay? There is no flow in this water. Is that fine?
Okay.
So how will my ink?
Yes.
How will the ink travel in the water? It will diffuse. धीरे-धीरे the entire
Yes,
water will
ma'am.
become blue. That's fine.
Okay.
ठीक है? So this is a for example of diffusion. ठीक है? You have understood how it goes?
Yes, sir. Yes, ma'am.
Then let's have another case. I have another. I have another bucket of water. Okay, now I'm taking it or just a bigger section of water. I put ink from here into my water. Okay, initially it's still. But what I do is I start stirring it. Okay, I start mixing this water. Can you do that? Right?
Yes, sir. Okay.
So now how is the ink going to travel? It's going to travel along with the water. Diffusion is going to be much slower than Like when I'm physically mixing it, what is happening that I'm causing the property, that is the ink,
Hmm.
that it just keeps on mixing because of the flow of the liquid as well. When I'm mixing it, I'm causing it to move, right? Because of the velocity.
Hmm.
So that is convection. When there is a flow, because of the flow, that is because of the motion of the fluid, when a property is being transmitted, that is called convection or
Hmm.
advection. Some people call it
Hmm.
advection. And if the travel of the property or the transport of the property is only due because of concentration, then that is called diffusion. So
Okay,
diffusion
ma'am.
is concentration. Okay?
Okay, okay, got it. And sir,
Great.
and ma'am, dissipation.
Dissipation. Okay.
Yeah.
So, okay, let me just write this down so that convection flow, right. So, okay, let us once again take a sort of an intuitive example. Okay, so you all use that tuning fork in your 11th, 12th. Use correct?
Yes. Yeah.
Yeah. So
Yeah.
then what happens? You just what you do is that you hit it, and then there is a right. Apurva, I'll come to that just a second. Um, And b square minus 4ac is not 0 in that. You see why it's not 0. Right. Sorry, Shipra, where was I? So if you have a tuning fork, then what happens is that when you suddenly, like you ring it against a metal table, and then it starts to vibrate, right? Then what
Hmm.
you do is that you hold it. So then the vibration dies down, right?
Yes.
That is called diffusion. Basically, the amplitude of the vibration or my amplitude of the disturbance, that becomes low. This is called diffusion. Like the frequency is supposed to be
Dip
same for this.
means dissipation.
Oh, sorry, this is called dissipation. Right? That basically the property is just dying out and spreading out. Okay?
Okay.
So
Okay.
the mathematical expression for dissipation and diffusion both happen to be something like this. Why? Because essentially the action of both is to sort of spread the property to a larger area or a larger volume than what it was initially there. Okay, even
Okay.
when you are stopping the force from vibration, you are essentially absorbing it, and when you are absorbing it, it dies down. So then that is called dissipation. Okay.
Okay. And ma'am, how physical, what physically it signifies and how it's mathematically signifies. So connection between them can be observed by observation.
It can be obtained mathematically as well. Okay, so for this you should do one activity. Now you've understood how to use Taylor series, right?
Yes, ma'am.
Okay, so then let's see, let's you have a grid like this. Okay, let's
Okay.
take a 4 by 4 grid. You have a 4 by 4 grid, that is you have 16 circles. Okay, so then
Okay.
what you do is that you put like a function x minus y or x square minus y square on all the boundaries. Okay, this is the condition on the boundaries.
Mm.
Okay, and all of these different points, or leave the boundaries. Just a second. Just give me an expression for, sorry, give me the expression for this. Okay,
Mm.
and dy square. Just give me the expression for this. Okay, derive it
Mm.
and see what that means. Okay, so then what you will observe is that there will be some sort of averaging. Use Taylor series for both of these activities. Okay, in fact, you don't even need to take a 6 by 6. Wait, sorry, I'm just giving you an unnecessarily tough problem. Just take a straight thing and just derive the expression for this term. Okay,
Okay.
using Taylor series. You have f, this is um, fx minus delta x, this is fx, and this is fx plus x. So use your Taylor series, get me this, not f5. Is it okay?
Yes, ma'am.
Hopefully I'm not confused you by changing the terms too many times. But then you just compute this value and then you will realize something from there. And then you tell me what you realize in the next session. Okay? Or you can mail
Okay,
me.
ma'am.
Not an issue. Right.
Your mail ID, ma'am.
Okay. I'm going to put um, the links for the various things that you require in the chat box once again.
Okay, ma'am.
Yeah. So, let me see. So you can find all information about me in my Google Drive. I've put a document which says hi. Okay, so just open that and see my email ID and whatever other social media handles, etc., etc. If you want to access me through those. Okay, fine. Okay, then what other question did we have? There is one question in last week assignment for eigenvalue. I'm not getting the answer. If it's in the assignment, then you have to do it on your own. If you're not getting anything, then they ask me a specific question using your mail. Okay, but I
Ma'am,
cannot. Yeah.
can you tell me how to solve these eigenvalue problems from PDs?
From
Like,
partial. Okay.
yes, yes.
So you're asking me what eigenvalues are.
Yes, ma'am.
Essentially, you know about characteristic equation that when you have a partial
Yes, ma'am.
differential. Yeah. So then you have something like d square minus d plus whatever 3, right? This any equation that you get a characteristic equation that looks like that, or d is like d square 5 by d square. So you know the characteristic equation, right? I'm not going to talk about that. So what answer we get from here, that is the eigenvalue. Okay, that's about it.
Ma'am, if our mixed derivatives are there, and
You will have to actually address that question to me properly over mail. If you do that, then I'll answer it. Right now, I'm not like that's a pretty long topic. So if you want, then we can then I can just point you to some resources where you will be able to get this information. This is like math stuff, so you will be able to get it in any engineering maths book. Just if you're not able to understand something very specific, then mail it to me or just yeah, just mail it to me. That should be okay.
okay, okay, ma'am.
Right. In last session on Friday, someone asked a question which was not answered. Yeah, I answered that question, Apurva. The question was that what is meant by diffusive? That when there was a question which went like parabolic governing equations are diffusive in space. So by diffusive, once again I mean that this term appears. Okay. That is because I said the action of the even derivatives is diffusive. So then when I see such a term in my equation, that means it is diffusive. Okay, so that is what the question was, that why are we calling it diffusive? We are calling it diffusive because there is a even derivative in space when we are looking at a parabolic governing equation. Okay, Pooja? Right. Question is b square minus 4ac is 0 for Laplace equation. So it is not 0 for Laplace equation because what is there is that a, let's have a look at our general equation once again. Again, Akshat, here you are using, I'm using 2b over here, which is why I have a different notation. Okay, so that is, I hope that's already clear, but I'm just writing that right down again. It's equal to f of phi x y d phi by dx or d phi by, sorry, dou phi by dou y. Okay, this is what the general equation looks like. So here, b square minus 4ac. So let me have a look at my Laplace equation. What does that look like? Laplace equation in 2D. Right? So what is over here? Oh, sorry, C. So what is it matching with? A is 1, okay? C is 1, and B is nowhere to be seen. I don't have a B. No B in Laplace equation. So what do I have over here? 0 square minus 1 into 1, which is equal to minus 1, which is less than 0, so it's elliptic. Is that okay? If Apurva is still in the call, then hopefully that has been resolved. It was asked for 1D. So basically what I have over here is that it's a 2D equation, and my general equation looks 2D, and I know what my Laplace equation means. So I'll stick with, okay. Did you lose your net, Annie?